average signal power is basically uh, mo- uh, what do it is drifting basically. Okay, so sometimes it is zero point 0.5, sometimes it is zero point 0.9, and sometimes it is 1. So when it is near to what we want to receive and what we are expecting to receive, and it is near to that, so that is the average power received by the digital signal is basically changing from time to time, from signal to signal. So that may cause receiver to decode. It will be difficult for the receiver to decode the digital signal correctly. So it may not be able to decode it properly because it will not understand what is the exact power level or what is the exact signal level, signal's power level. Okay. So I think we discussed DC current. No,
No,
we
ma'am.
did. Okay, so DC components, as we discussed that, because now because we said that digital signals can be represented with some discrete values, some static values. So when I am saying I am representing one as some x volts and zero as some other some y volts, then we say when we think or we say that it is all having some constant voltage level. So whenever we are talking of a constant signal, a constant voltage or power level, then the spectrum will not have any variation in the frequencies, and it will only have a very the spectrum will only have low frequencies. The frequency spectrum will not have a variation in the frequencies f1, f2, f3, fn, and there will not be any change in the frequencies, and only will have one static voltage level, power level, and only one lower frequency level will be there. So that these frequencies are nearly zero, not zero but nearly zero, because frequency is what, the change in the cycle or the pattern of sine wave in one time unit. So because there is no change in the amplitude, there is no change in the sine wave, so it is a direct current and you will have a static voltage, then therefore it has only low frequencies, and this is nearly zero. So sometimes what happens, we have some filters through which the current has to pass, the voltages have to pass, the signal has to pass. So some systems, they may not allow low frequencies to pass through those receivers or those transmission systems, transmission media. Therefore, that could be one of the problems with digital signaling when we are using only two voltage levels, static voltage levels and DC components to represent the digital signals. So now we are discussing the problems with the digital signals. So if we are not using any, because yesterday we discussed, is there only one? Okay. So we were discussing the line encoding scheme. Line coding, we discussed that we were representing the static voltage levels, like one was representing some minus V volts and zero was represented by one data element, that is plus X volts or plus Y volts. So we were saying in line encoding, we can represent one as some static voltage level and zero as some static voltage. This was digital signaling actually for digital data. But these are the problems and the characteristics of digital transmission when we are doing. So bandwidth is not the same as we calculated. We said we have to find out the effective bandwidth, which is finite. Fine. So another characteristics of digital signaling is baseline wandering, which we discussed yesterday. Now, this is another characteristics of digital signaling, that is DC components. So while doing digital signaling using only two voltage levels, X for 1 and Y for 0 volts. So if we have only two voltage levels, that creates DC components. And having a DC component for digital signaling will mean that it will be of almost zero frequency or low frequencies, which may be blocked by the transmission media or your electrical signaling system. Now, one more problem with DC components is 0-1 parity, because if you have baseline wandering, which we discussed yesterday, if baseline wandering is there, then we may interpret one due to some electrical spikes and electrical coupling. Suppose some electrical signal which is being passed through the transmission media, coaxial cable, the bit may be represented wrongly because of some sudden spike in the electrical signal. So the power level goes up, and but that bit in which the electrical spike occurred, that on in that time duration, if you have passed suppose 5 bits, they have to be because the actual data, suppose it was 5 zeros, but it would be represented as 5 ones. So that is because of the baseline bonding in DC components. Fine. So, and a long distance link may use one or more transformers to isolate different parts of line electrically. So that could be another problem, because you may be using transformers. Transformers are also having some amplifiers in between. So if you are doing long distance communication, so we'll be using the electrical lines and the transformers also for long distance communication. So for these systems, we need a scheme with no DC component, because DC components have all these problems of baseline wandering and zero frequency components, and which and the transformers and those filters, electrical filters, may not interpret these low frequency components or zero frequency components, so they will not allow to pass the low frequencies. So these are the problems with the digital signaling when we are only using static voltage or discrete voltage levels for digital signaling. Then another problem is self-synchronization. So either your coding scheme, digital coding scheme should have self-synchronization, or otherwise they will lack synchronization. What do you mean by synchronization? Suppose the basic analogy from real life is, suppose I am delivering my lecture at a normal speed and at a brisk speed, that is fine with every student, then that will be okay. But if I am running too fast and I am having hyper speed, and I am running on a sonic speed, and I am delivering my lecture on a sonic speed, most of the students will not be able to synchronize themselves with the speed. There may be some students who may have joined the class late, so they may not be able to synchronize themselves what we are discussing, because they don't know the base. So there should be some mechanism to align and to synchronize yourself with the sender and the receiver. Similarly, in digital signaling, when the sender's speed is too fast, when it is sending it's very at a faster speed than which is handled by the receiver, then it will be a problem, because there will be no synchronization, and the bit interpretation at the receiver side will be different as sent by the sender. Moreover, it could be like sender could be slow also, but the receiver hardware could be efficient, and it could be a faster hardware. Then also there will be a problem, because there will be no synchronization. So one bit, suppose the sender has sent 2 bits in the same time duration, because the clock duration of both the clock at both the sides, sender and the receiver side, will be different. So if the receiver clock is faster or slower, the bit intervals are not matched, and the receiver might misinterpret the signals. So that is the problem. Now you can see the example here, effect of lack of synchronization. So the sender has sent this one bit in this time duration, but this clock of the receiver is very fast. So what it has done is, it has had it is very fast, and the clock has almost more than 1.5 bit duration it has crossed when it has finished the first bits, sending the first bit. Can you see in figure 4.3, A and B part? In A part, the sender is sending, and the bit duration at the sender side is more, but the clock at sender's receiver side is fast. So you can see these 2 bits, 1 and 1. So instead of because we are sending the constant DC voltage level, because the sender is sending constant voltage of for 1 volts, some positive voltage. So the receiver clock for that duration is receiving a high voltage, so it will interpret 2 ones, because its next bit has also started, its next clock cycle has started. So the next bit will also be represented as 1. Now in this duration, during this duration, it is sending a low voltage. So low voltage for 0 bit, it is the protocol says it should represent low bit as low voltage level or negative voltage level as 0. So for this duration, it will interpret 0 as 0 only. But again, when the second 0 has been finished by the sender, it has also finished. So sender has sent 2 bits in the same time duration. The receiver clock has clicked for clock. It has basically counted for 3 times. So it has sent 2 bits, but the receiver has interpreted as 3 bits. But its clock has counted 3 times. So it has interpreted as 110. Again, the sender is sending only 2 bits in the same time duration, and the receiver is receiving high voltage for these 3 clock cycles, 111. So it is sending 2 ones, it is interpreting it as 3 ones. Similarly here, it is sending continuously low negative voltage for zeros for this entire duration of 3 clock cycles of the sender. But during this time, when the sender has counted 3 clock cycles, it has counted more than 4 cycles. So they are interpreted as 4 zeros. Similarly, this one, so in the middle of this last second clock, it has changed the voltage level, and now it will be represented as 1 and 1. So the message was 10111001, but the sender has interpreted the message as 110111, 4 zeros and 11. So you can see this is an error in communication. So this is because of the clock synchronization of the sender and the receiver. I hope this is clear to all of you.
Yes, ma'am.
So a self-synchronizing digital signal includes timing information in the data being transmitted. So we'll see some later on in the next section. We'll discuss some of the encoding schemes in digital signaling which uses self-synchronization, so that there is no synchronization problem. And even if there is some flaw or there is some fault on temporary basis, and the clock is out of phase or clock is not synchronized, then also after each bit it can or after a few bits it can also synchronize, and at least it can repair the error in communication. So that is done in the coding schemes we'll discuss later in the next section. Now this is another example for finding out how many bits are transmitted wrongly. So in a digital transmission, if the receiver clock is 0.1% faster than the sender clock, how many extra bits per second does the receiver receive if the data rate is 1 kbps? And how many if the data rate is 1 mbps? So at 1 kbps, the receiver receives 1001 bits per second instead of 1000 bits. Why? Because we are saying 0.1% faster. So 0.1% faster means 1 bit extra in the entire message in 1 second. Okay, so instead of sending, because my data rate is 1 kilobits per second, 1 kilobits per second means 1000 bits per second, and 0.1% faster in 0.1% faster means 1 bit is extra. So 1 bit is extra in this 1 second. So instead of 1000 bits per second, the receiver has received 1001 bits per second. Similarly, if we say 1 Mbps, the receiver receives 10 lakh and 1000 bits per second instead of 10 lakh bits. Okay, so the sender has sent 10 lakh bits and the receiver has received these many bits. So these 1000 bits are extra. Why this 1000 bits extra? Because there is 0.1%, the clock is 0.1% faster. So for this is for 1 second, for a 1 Mbps, because the data rate is more. So for a 1 Mbps data rate, you'll have 1000 bits which are extra received by the receiver. So this was the error because of synchronization in the sender speed and the receiver speed. Now built-in error detection. Now there are some errors which are, so we should have some characteristics in the encoding scheme only, and that should be built. We'll be discussing it in the next layer, data link layer and network layer. So we have some error detection algorithms also. So we should have, during the transmission, if we have some error, we should have some capability to detect that error and rectify that error. So some schemes already have this built-in capability to some extent. Not all the 100% errors cannot be detected, but still some schemes have error detection mechanism inbuilt. Then next characteristics of digital signal should be immunity to noise and interference. So a desirable characteristics for any digital code should be that it should be immune to noise and other interferences, and this we'll discuss side by side when we'll be discussing the streams. complexity. So when we are saying coding scheme is very efficient in terms of error detection, immunity to noise and interference, and it is very efficient in terms of synchronization and all. But still, on the same side, we should be also be able to find out the complexity of the scheme, coding scheme, because if it is a simple one, then it is good, it is easier to implement, this is less costly. But if it is complex, it is suppose it is the example is, if we have only 2 levels for implementation and interpretation, the hardware will be very simple and it will be less costly. But if we have more number of signal levels, suppose 4 or 8 levels or 16 levels, the hardware accordingly should be able to receive the signals at different levels and to interpret them at different levels. So that will be more complex hardware and that will be more costly also. So that all these things we have to consider while doing the encoding, while implementing the encoding schemes in the physical layer. Now, what are the different line encoding schemes or coding schemes? So roughly we divide them into 5 broad categories, and the categories are unipolar, polar, bipolar, multi-level and multi-transition. So we'll be restricting ourselves to the first 3 ones in this syllabus: unipolar, polar and bipolar. Fine. So unipolar, what do you mean by polarity or polar? Any idea? Polarity or polar? Anyone?
Ma'am, basically the development of the two oppositely charges, that's like positively charged or negatively charged due to some electrical field or magnetical field. So,
Yeah.
ma'am, yes, ma'am.
So when we have only one sign, one polarity, either positive or negative, that is unipolar. Either only positive or only negative, that is unipolar. When we have 2 polarities, 2 opposite polarities, 2 different signs, negative voltage and positive voltage, that is polar. Any one of them. And then bipolar means both of the polarities. It also the same signal can have positive also, it can have negative also. So this is these are the 3 schemes for line encoding in physical layer for encoding of the digital data. So what we are discussing right now, I think so this is kind of what I am doing now. Right now is the next sentence would be for synchronization. So I am sending the data continuously, I am discussing the things continuously, but some of the students are lost, they don't know what we are discussing in the class, what we have discussed in the class yesterday. So they must be lost and they must be wondering what's happening, what is ma'am discussing, why these are important. So I'll, for again doing synchronization, sender and receive synchronization, I would like to tell you that we are discussing digital data to digital signals. Okay, so we have to send the digital data which is stored on our laptops or computers or mobile phones in the digital form, that is zeros and ones forms, bits forms, and we have to transfer the data through digital signaling to the other end. So when in the network communication on the computer network, we have to send the digital data and we are doing digital signaling also. The carrier is also digital. Then we have to use the line encoding schemes. So we are discussing the physical layer encoding schemes for transferring digital data over digital signals. Is that clear to those who were not in synchronization with me? Students, what we are discussing, is it clear?
No.
Fine. So we have discussed 5 things: unipolar, polar, bipolar, multi-level, multi-transition. So now first one is unipolar. So unipolar schemes, they all the signal levels are on one side of the time axis, either above or below. That means either positive or either negative. Only one thing. So the first scheme in unipolar is non-return to zero. Traditionally, a unipolar scheme was designed as a non-return to zero scheme in which positive voltage defines bit 1 and the zero voltage defines bit 0. It is called NRZ because the signal does not return to 0 at the middle of the bit. So you say this is the bit interval, the entire bit interval for the 1. So from this point to this point, is my mouse visible?
Yes, ma'am.
Okay, so this is 0 volts time axis and this is the amplitude of the wave or amplitude of the signal. So if it is a signal we are transferring 0 volts, and V volts is the highest amplitude. So if we are sending V volts for the entire bit duration, it will be treated as 1. And if we are sending, if you're not sending anything, then it will be treated as 0 bit. So if it is 0 volts or it is the absence of the signal, that will be treated as 0. So now we can see what is the normalized power. This is half of V square plus half of 0 square, half of V square, because for once we are sending the voltage. And why half? Why half? V square by 2.
I'm taking only positive signals.
Yes, because we are taking only the unipolar. Okay, so half of V square for this bit, half of 0 square for 0 bit. No signal, no power. Okay, so normalized power will be half of V square. Now, compared with its polar counterpart in the next section, this scheme is very costly. Why it is costly? We'll see that the normalized power for 1 bit per unit line resistance is double that for polar NRZ. So when we'll be discussing the polar scheme, we'll see this is using the full power for sending one electrical signal. So for sending 1 bit, even if we are not sending any voltage or any signal for 0 bit, absence of signal will be treated as 0 bit. But for at least sending 1 bit, we'll be using the full power and full amplitude. So full DC component has to be sent. So it is using the double power. We'll see how it is double. So now in polar schemes, we can use both the sides, positive and negative side on the time axis. For example, the voltage level for 0 can be positive and level for 1 could be negative. Why it is non-return to 0? Because if it is positive for 1 and negative for 0, we are not in the middle of the bit, we are not returning to 0 level. So it is either positive or negative. So in polar NRZ, so this was also non-return to 0 because we were not returning to 0 in the middle of the bit. Fine. So it is also NRZ, but this is polar scheme. Now in polar NRZ, we have two schemes, NRZL and NRZI. One is known as non-return to 0 level and non-return to 0 invert. In NRZL, the level of the voltage determines the value of the bit. In the second, the change or lack of change in the level of the voltage determines the value of the bit. So if there is no change, the bit is 0. If there is a change, the bit is 1. Let's see what does it mean. So polar NRZL and NRZI schemes. NRZL, 0 bit is represented as positive voltage level. 1 bit is represented as negative. You can have vice versa, no problem. So normally we can take 1 as positive and 0 as negative. That's up to you, entirely up to the coder or the protocol. So non-return to 0 level means we are having a specific level for a bit, but duration of this one bit, with duration of time or this clocks in the full cycle, full pulse clock cycle of duration of this bit, there is no change in the voltage level. So that means non-return to 0. So during the whole bit transfer, there is no return to 0. That's why it is known as NRZ. L means level. So it has a particular level for 0 and particular level for 1. And polar means it can have positive and it can have negative. So I hope it is clear what is meant by polar NRZL. So now my scheme says 0 has a positive voltage, 1 has a negative voltage. So 0, if I am transmitting 2 zeros, it will be 2 positive levels. If I am transmitting a sequence of ones, it will be all negative voltage throughout all those clock cycles, and then 0 for positive. This is NRZL. Now we did some variation in the NRZI. So if there is a next bit is 1, we'll do transition जहां पर भी हम हैं, पॉजिटिव है या नेगेटिव, किसी भी वोल्टेज लेवल पर है, उससे प्रीवियस बिट कुछ भी था, 0 था या 1 था. अगर 0 था तो हम पॉजिटिव वोल्टेज लेवल पर होंगे, एंड अगर 1 था तो we would have been at the negative voltage level. So whatever is the current voltage level according to the previous bit, the next bit, if it is 1, will do a transition from that voltage level to the next level. But if the next bit is 0, we'll not do transition. Got the point? So previous bit, suppose I started with 0 as a high level, positive level, and now my next bit is 1. I'll do a transition from positive to negative. Because it is polar, it is using both the schemes. But now NRZI is not using positive for voltage for 0 and negative voltage for 1. There is no definition positive and negative for zeros and 1. There is no specific rule that 0 will have positive and 1 will have negative. We'll only say we started the signal as a positive level for 0, but if the next bit becomes 1, you will do transition from positive to negative. Now after this current bit was 1 and it was at negative, if the next bit is 0, there will be no transition and it will continue at the same negative level. Again next bit is 0, it will continue with the same negative level. But after 0, the next bit is 1, the sender will change and transit from negative to positive level, and it will send a positive voltage. Again after this one, there is another one, so we'll change the level and send the negative voltage. Again after this, there is a 1, you'll change from negative to positive and do a transition at the positive level, and you'll transmit the positive voltage. But after this one, you don't have to do a transition from positive to negative. It should be constantly positive because next bit is 0. I hope this is clear to all of you.
Yes, ma'am.
So inversion or the change of polarity will be only done when the next bit is 1. So sender will only do transition from positive to negative or negative to positive if the next bit which is to be transmitted is 1. Otherwise, it will remain at the same level, whatever it is. If it is negative, it will be continued as negative. If it was positive, it will be continued as positive. That is NRZI. Now, what is the basically characteristics of this? And you can see the frequency spectrum is this, and power level is on the y-axis. R is equal to 1, S average is n by 2, and the bandwidth. Now you can see the bandwidth and the spectrum here. Most of the frequencies and the bandwidth is constrained within this curve, under this curve. So that is the problem with this scheme, that most of the power is concentrated between this bandwidth. So that is, we will discuss in a short while. Now let us compare the schemes. We defined so many characteristics and criteria. So we discuss, just hold on for a moment. So, where we just hold on. So, let us compare the two schemes, NRZL and NRZI. So, although baseline wandering is a problem for both the variations. Now, suppose baseline wandering is still here. So, and if it is, suppose for positive, suppose V volts, we are getting. Suppose 5 volts we have this for 0 and -5 for 1, and we are not getting the exact 5 volts, we are having something else. So continuous zeros and continuous ones may be interpreted as some different values. So it may be because of that baseline wandering is a problem with both of them. But and in NRZL, when we have NRZL, it is a problem because continuously the same voltage for the same bit. Suppose we have continuous ones and continuous zeros, then baseline wandering can be a problem for continuous zeros and continuous ones. Okay. Another thing is, if there is a long sequence of zeros or ones in NRZL, the average signal power becomes skewed. So as we have seen here, the average power, signal power is skewed. So it is more concentrated towards the this half, left part. Okay, so the receiver might have difficulty discerning the bit value. In NRZI, this problem occurs only for a long sequence of zeros. If somehow we can eliminate the long sequence of zeros, we can avoid baseline wandering. We'll see shortly how it can be done. So you can see a long sequence of zeros and long sequence of ones. So this power is more concentrated in this part. So positive, if we are having continuously zeros, then the power is more consumed here as compared to when we are sending one. So if we are sending one, so less power will be used. So power is more towards zeros, continuous sequence of zeros. So this is Q. Then synchronization problem. The sender and receiver clocks are not synchronized. It also exists in both the schemes. So still now what we have discussed is synchronization, but there is a problem with this because we are not doing transition in the middle of the bit. Therefore we have also a problem, the same problem we discussed for synchronization. So this is more serious in NRZL than in case of NRZI, and with the long sequence of zeros it can cause a problem in both the schemes. A long sequence of 1 affects only NRZL. Why? Because synchronization will have more problem in NRZL. Why? Because it is constantly saying we have to send a positive signal for 0, we have to send a negative voltage signal for 1. So if we have a continuous 0, 0, 0s, continuous positive level, there could be a problem in synchronization. And if we have continuous negative voltage, we can have a synchronization problem. But because in here, if we have continuous zeros, there could be a problem. But in case of ones, we don't have any problem because for every one, we are inverting the bit. So if it is a long sequence of ones, there is no problem because for every one, for every next one, we are doing the transition from negative to positive or positive to negative. So NRZI is less affected by the synchronization scheme, or it has less synchronization problems because it is kind of self-synchronized. बिकॉज अगर आपको पता चल रहा है कि कंटिन्यूसली बहुत जीरोज आ रहे हैं और आपको एकदम से अब नेक्स्ट एटलीस्ट हाफ ऑफ द स्ट्रीम ऑफ डेटा कैन बी सिंक्रोनाइज्ड. सो जहां पर भी आपका 1 आ रहा है वहां पर आप सिंक्रोनाइज कर पाओगे कि ओके यहाँ पर वोल्टेज लेवल चेंज हो रहा है, यहाँ पर ट्रांजिशन हो रहा है नेगेटिव टू पॉजिटिव या पॉजिटिव टू नेगेटिव, तो इट शुड बी 1. और जहां पर ट्रांजिशन नहीं हो रहा है वहां पर वो जीरोस है. सो यहाँ पर आपको प्रॉब्लम आएगी जहां पर जैसे ही ट्रांजिशन हुआ आपने उसको 1 इंटरप्रेट कर लिया, जहां पर ट्रांजिशन नहीं हुआ वो आपका सारा कंटिन्यूसली जीरोस है. सो लॉन्ग सीक्वेंस ऑफ जीरोस में सिंक्रोनाइजेशन की प्रॉब्लम आएगी. वहां पर आपको नहीं पता कि 2 बिट्स ट्रांसफर हुए हैं कि 3 बिट्स ट्रांसफर हुए हैं, लेकिन जैसे ही आपका ट्रांजिशन हो रहा है यू आर चेंजिंग इट टू you are interpreting it as 1. So whenever you have any synchronization problems, you can resolve it in NRZI a little bit when we have alternating zeros and ones. That is automatically resolved in the signal itself or signaling scheme itself, or otherwise if we have continuous streams of 1 then also it is resolved to some extent. But when we have continuous streams of zeros in the signal, then there will be synchronization problems and you don't have any inbuilt method to remove this synchronization problem using NRZI also. So then another problem with NRZL occurs when there is a sudden change of polarity in the system. Now suppose there is sudden spike or there is some polarity change because of the external factors, physical factors. So you have a electrical line going on, you have a cable which is running from one end of the room to the other end, and there are some some power spikes in the electrical system, or maybe some interference by the wiring which is near to your communication line. So there are 3-4 lines which are lying simultaneously. So there could be electrical interference because of that. So in that case, if you have this problem, you have more problem that will be in NRZL, because we are only having different polarities for zeros and ones. So instead of sending 0, because we are sending 0 as positive volt and there is sudden change in the polarity due to some external factors not in your control, then it may happen that instead of positive voltage you are sending the negative voltage, or it becomes negative, it becomes low. Again, there is some sudden change in the polarity, and instead of negative, it becomes positive. So the bits, series of bits, zeros and ones, they may be misinterpreted due to the polarity changes due to the external factors. Now, so if twisted pair cable is the medium, a change in the polarity of the wire results in all zeros interpreted as ones and all ones interpreted as zeros. This is one problem. NRZI does not have this problem. Both schemes have an average signal rate of n/2 baud. Now, NRZI will not be affected by the polarity change because we say the level will change. We are not fixing the level positive or negative for zeros and ones. So this is not affected by the polarity change. So we haven't fixed that 0 is positive and 1 is negative, or 0 is negative and 1 is positive. So the transition from positive to negative will be 1, or negative to positive will be 1. So the transition will make the difference for interpretation of 0 and 1. So next is, let us discuss the bandwidth also. So here we see this bandwidth. Here we are having more power concentration. Here we have less power concentration, and the total bandwidth of the signal is only focusing on the left half. More of the bandwidth is in the left half, not in the right half. So this is total bandwidth of the signal is not divided proportionately or evenly. So this is not a balanced bandwidth spectrum. So it also shows the normalized bandwidth. The vertical axis shows the power density, the power for each 1 hertz of bandwidth. The horizontal axis shows the frequency. The bandwidth reveals a very serious problem for this encoding. The value of the power density is very high around frequencies close to 0. So this is the frequency, and so nearly 0 frequencies or near 0 frequencies have the highest power, and which have higher frequencies after 0 and between zeros and ones, they will have towards 1 and 2 frequencies or higher frequencies, it has low bandwidth. So the spectrum is more towards nearly 0 frequencies. So this means that there are DC components that carry a high level of energy. So as a matter of fact, most of the energy is concentrated in frequencies between 0 and n/2. So this means that although the average of the signal rate is n/2, the energy is not distributed evenly between the two halves. So most of the frequencies which are nearly 0, so more power is concentrated there in this schemes. So they have a DC component because this is a constant value, this DC component, positive or negative, or positive to negative or negative to positive. So every time whatever we are sending is, we are sending a DC signal, nearly 0 frequency signal, and more power is concentrated near the 0 frequency signals because of the DC component present in NRZ and L and NRZI schemes, which are polar schemes. Now example for calculating the average signal rate and minimum bandwidth. Now signal system which is using NRZI to transfer 10 Mbps of data, what are the average signal rate and minimum bandwidth? So S is n/2, so which is 500k bauds. Why? Because bits per second can directly be mapped to the signal rate, which is computed in terms of baud. So n/2, we say n/2, so 10 Mbps is divided by 2, and that is 500k baud. So this is 10 into 10⁶ bits per second, and divided by 2, that becomes 500k bauds. Is that clear?
Yes, ma'am.
Okay. So then we have, okay, so minimum bandwidth for this average baud rate is S is equal to 500k hertz. So frequency will be equal to S, this bandwidth will be equal to S only, which is 500k hertz. So instead of k baud, the frequency is always measured in terms of hertz. Hertz is unit of frequency, which is 1 upon time. So this is how many signals per unit of time, bits per second, and this is 1 upon time, this is hertz. So k baud, instead of k baud, it will be k hertz. Now return to 0. Okay. So polar schemes we are discussing, which uses two levels, plus level, that is positive level and negative level. So in this we discuss the first scheme, non-return to 0, which is again divided into two parts, and NRZ-ln, NRZ-I. Now we are discussing return to 0, RZ. So the main problem with NRZ encoding was when the sender receiver clocks are not synchronized. Fine. So receiver does not know when the one bit was ending and the next bit is starting. So we have a solution for that, return to 0 scheme, which uses three values, positive, negative, and 0 also. So in the middle of the bit, so in our RZ scheme, the signal changes not between bits but during the bit. So we can see here. So this is the duration of the bit, 0 bit, from this point to this point first. And if we have to represent 0, return to 0, so in the middle of the bit, this is the middle of the first bit, 0 bit. So signal is changing its polarity. Because it is a polar scheme, it is changing the polarity. So from negative to then 0 to the positive. So we say, if we have to represent 0 in polar RZ, for 0 bit, suppose this is my interpretation, that for 0 it should be negative to 0 to positive. So there is a transition in the middle of the bit. So it is for synchronization. So then next is 1 can be represented as positive to then 0 to negative. Got the point? Then 0, negative to then 0, but negative to 0 is in the middle of the bit. Then negative to 0, then it is going to the positive if it is from positive to 0. So it is always returning to 0. Basically, when we are saying we are representing 0, it is either positive to 0 or negative to 0. So that is 0. Or 1 is also same, negative to 0 or positive to 0, but that is in the middle of the bit. So it will be, how it will be used for synchronization, we'll discuss in a short while. So return to 0 scheme. So it remains there at 0 level until the beginning of the next bit. So the main disadvantage of RZ encoding is that it requires two signal changes to encode a bit. So now you can see, if we have to represent 1 in figure 4.7, if we have to represent 1, it is representing a positive voltage level and 0 voltage level. And for 0, we have two signal levels, negative voltage level and 0 voltage level. So for every bit representation, the signaling speed has the signaling rate has been doubled, because for every bit representation we should have two signal levels. So the complexity has increased and it is occupying the double bandwidth. We have to do signaling at a double rate for representing bits like this. So this is basically the disadvantage, but it is synchronized, because at the receiver side, if we say after in the middle of the bit it is changing the polarity, then it will be interpreted as 0, and then again if it is not if it is 1, then it is changing from positive to 0, it remains at the 0 level. So it will be synchronized using this scheme. The same problem that we mentioned, a sudden change of polarity resulting in all zeros interpreted as ones and all ones represented as zeros still exists here, but there is no DC component problem. So there is no constant DC problem, क्योंकि आपका zeros भी होगा या one भी होगा. Suppose one भी है, तो every time if it is a continuous one, we are changing it like positive to 0, then फिर positive to 0. If it is again 1, then positive to 0. Fine. And if it is continuous zeros also, negative to 0, negative to 0, negative to 0. So if it has continuous zeros and continuous ones, then also we don't have a static DC component and continuous DC component. So my bandwidth is evenly divided as shown here on the right hand side of figure 4.7. You can see the graph. The bandwidth is evenly divided in the entire spectrum of frequency. So it is at one almost at frequency 1, This is the middle of the bandwidth, and nearly zero frequencies, they have less power, they contain less power, and nearly zero and high frequency too, it will be power will be less. So the spectrum is evenly balanced and it is divided evenly. Now another problem with RZ is it uses 3 voltage levels. 0 level also for transition in the middle of the bit, and positive and negative for zeros and ones. So as a result of all these deficiencies, we never use it in practical purposes for digital signaling. So instead these are replaced by 2 more efficient schemes, Manchester encoding and differential Manchester encoding. So idea of return to zero transition at the middle of the bit and the idea of NRZL are combined into Manchester scheme. And idea of RZ and NRZI are combined to get differential Manchester. So RZ says there should be a synchronization and there should be a transition in the middle of the bit, that the bit is changing. So whenever we are changing and we are transiting in the middle of the bit and remains at 0 level, at the same level, that means we are changing the bit. So if the clocks are not synchronized at sender and the receiver side, they can re-synchronize themselves, and if there is a transition in the middle of the bit, the receiver will get to know that the next bit has changed. So that ways they can re-synchronize after some time, and they will be synchronized. But there was a problem with RZ that it was using it, and that it was having this sudden polarity change was a problem, and one more problem was there. It uses 3 voltage levels. Okay, so NRZ and NRZL have so many problems because the more power was concentrated towards nearly zero frequencies, and less power was towards the higher frequency components, and it has a continuous DC component also. So these were all problems with NRZL and NRZI. So all these problems will be resolved in differential Manchester and Manchester encoding. So differential Manchester encoding, it says the bit is divided into 2 halves and the voltage remains at one level during the first half and moves to the other level in the second half. In the transition at the middle of the bit provides synchronization. Similarly, in differential Manchester, if the next bit is 0, there is a transition. If the next bit is 1, there is none, like NRZI. We'll see. Now, suppose 0 is represented as high to low, but it is through the 0 level. Fine. And 1 is low to high. So Manchester encoding is in the middle of the bit, it is doing a transition. So why we are going from high to low through 0? Because we wanted something like RZ, return to 0 scheme, because we wanted the synchronization. So this 1 bit during this entire duration of clock cycle, my 0 bit is to be transmitted. So I am doing a transition in the middle of the bit from high to low, that will be represented as 0. From low to high, that will be represented as 1. The next bit is 0, high to low. Next bit is 0, high to low. Next bit is 1, low to high. Next bit is 1, low to high. This is, here we have resolved the problem of DC component also, because in the middle of the bit we are doing transition. Fine. And we are also doing synchronization. Then differential Manchester, it says no inversion if the next bit is 1, and if the next bit is 0, we have inverted the polarity. So suppose in this bit I was sending low to high. Suppose there is no scheme like this, that for 0 it is high to low and for 1 it is low to high. But differential Manchester says only you will have to invert the level or invert the polarity when the next bit is 0. So suppose this was the something going on, negative to positive. If next bit is 1, it will remain at the same level, but in the middle of the bit it will be doing transition from high to low. Why it is doing from high to low here, if we are not saying 1 is high to low? Because we have to do transition in the middle of the bit for synchronization. So this transition in the middle of the bit is for doing synchronization. This is not for representing zeros and ones. Now next bit after this low level is 1. Therefore, we have to do a transition in the middle of the bit. And we have to invert the bit. So next bit is 0. So this black dot means next bit is 0. So we have to invert the level. So currently we are at level negative. We will have to invert the level to positive, and positive to negative, one transition. This is for 0 bit. So we are not saying for 0 we are doing high to low. We are just doing in the middle of the bit, we are doing transition for synchronization. But because when the next bit is 0, so now I have also come here negative part. So I'll do a transition immediately at the start of the bit. I'll go from negative to positive, and again I'll do in the middle of the bit, I'll do the transition from high to low for representing that bit that I have completed one bit. This is for synchronization purpose. Then another one is 1. So I was already at negative level. I will not do transition at the start of the bit. I will not invert the polarity at the start of the bit. But for synchronization, I will have to go from high to low or low to high. So I will make a transition in the middle of the bit. So I was already at negative. So at the middle of the bit, I'll do transition from low to high. So next bit is again 1. I will not do any inversion at the starting of the bit, but in the middle of the bit, I'll do transition for synchronization from high to low. This is known as differential Manchester encoding. So we are doing transition in the middle of the bit, which is used for synchronization. Fine. So minimum bandwidth of Manchester and differential Manchester is 2 times that of NRZ. Why? Because हम बार-बार middle of the जो है bit में transition कर रहे हैं high to low या low to high, और दोनों में ही Manchester में भी और differential Manchester में भी a single bit 0 or 1 is using 2 different signaling levels. So positive and negative. So this is basically using double the bandwidth. Okay, 2 times that of NRZ. Now the last one is bipolar schemes, in which we have we use 3 levels: positive, 0 and negative. So bipolar encoding, sometimes called multi-level binary. There are 3 voltage levels: positive, negative and 0. So voltage level for one data is at 0, while the voltage level for other elements alternates between 0, positive and negative. So we'll discuss these schemes. There are 2 schemes, AMI and pseudo ternary. So AMI uses 0. For 0 it is using constant 0 level. For 1 it is using high level. For continuous zeros it is using 0, and for 1 it is making the transition negative, because this 1 was previously, for 1 we used positive, now for next one we will use negative, and 0 is always represented as 0. So for AMI we say alternate mark inversion. So alternate once